Hi guys, welcome to our third video in chapter 10. This video concerns 10.3 reactions in aqueous solutions. This is our final video for chapter 3, so this was kind of a shorter video, and it's leading directly into our discussion of the mole in unit 11. So to begin our discussion of reactions in aqueous solutions, let's go over a few quick vocab words. First, a solute is the substance that is being dissolved. The solvent is the substance that the solute is dissolved in. So a quick rule of thumb is that you will always have more solvent, so more solvent than solute, right? So you'll always have more of the thing that's doing the dissolving. An aqueous solution is defined as a solution where the solvent is water. And I'm going to highlight this next sentence. This is pretty important. Water is called the universal solvent because of how easily it can dissolve many other substances. No other substance that we know of dissolves as many different compounds and molecules as water does. The reason water is such a strong solvent is because it has that really strong polarity in the water molecule, and it can undergo what's called hydrogen bonding, which we talk about in chapter 13. I just have a couple of quick pictures to show this, right? So our water molecules, when they're just sitting around, they are going to orient themselves to have an attraction between the partial positive hydrogen and the partial negative oxygen of a separate molecule. And this is your actual hydrogen bonding, and it's caused by the extreme polarity of your water molecules. Now, that's all cool, but when we put an ionic compound or anything that is a polar molecule or an ionic compound into water, that extreme polarity is going to allow your water molecules to interact very strongly with your solute, and it's going to make it very easy to dissolve things in water. I have an example of sodium chloride being dissolved in water right here. You can see the hydrogen bonding in the picture above, and in the picture below, you can see how your chloride ions are attracted to the positive hydrogens on the waters. And that's why near almost all of your chlorides, you have those hydrogens oriented towards the green particles. Likewise, your blue sodium ions are positive and therefore are attracted to the red negative oxygens on your water molecules. And the fact that these water molecules are partially charged and have that polarity is what allows them to interact with these ions. So that's why it's such a useful solvent, why water is so useful. And then this next part over here is equally as important, right? Most reactions that we do in our chemistry in the universe, actually, not in the universe, but the chemistry on Earth are done in solutions, right? As chemists, when we do a chemical reaction, usually it's done as a solution because this means the particles are free to move around and collide, and the particles can slide around, right? In order for a bond to form, well, the atoms must be literally next to each other, need to physically contact each other to actually form that bond. And being in solution gives them the mobility to do that. When they're solids, the particles aren't moving. When they're gases, the particles are moving too fast to collide often. So the most efficient way to run a reaction is in solution. Water is not the only solvent, but it is the most common one. Okay, so let's talk about how we denote an aqueous solution. It's very straightforward. Let's say we have some hydrochloric acid gas and we would like to pump that into water. Well, we bubble it into water and it's going to dissolve, and your H plus ions will separate from your chloride ions. And we denote that it's aqueous with this little AQ. That means that the phase this is in is aqueous or dissolved in water. You can actually see that also with our sodium hydroxide in the example below. It's AQ means dissolved in water. So I'll just make a note quick. AQ means dissolved in water. All right, so that's how we denote it. Cool. So moving on, let's talk about some specific types of reactions that you might see in aqueous solution. And the first and honestly one of the coolest reactions we'll see is a reaction that forms precipitates. Remember from the last video that a precipitate means a solid produced by a chemical reaction occurring in a solution. We're going to do this often because it's very cool looking. And I have an example for you here, and we'll do some examples in lab. So yes, it's watermarked. I just ripped this right off of Google, but it still shows you take some copper to chloride, you mix it with sodium hydroxide, both of which are initially aqueous, right? So I can see if I take a look at your phase, your sodium hydroxide and your copper to chloride are both aqueous. And the sodium hydroxide is in this beaker. It's normally clear. and your blue copper 2 chloride is in the speaker. And you can see as we add them, we're forming this cloudy substance here. And you can see it's actually a solid and it still has the clear liquid over top in this picture. And that solid that's formed is your copper 2 hydroxide, which is insoluble in water. So that means insoluble water means that when it's formed, it is going to precipitate out and form a solid crystal, which is beautiful. And that's why this is so fun to do. And then we, of course, produce a sodium chloride molecule, or I'm sorry, a sodium chloride formula unit, which is in aqueous solution still. Cool. So that's reactions that can form precipitates. Some more vocab words here. We have shown thus far all complete ionic equations, which are just chemical equations that show all the particles as they really exist in a solution. But if we look up at this example, my sodium hydroxide combined with my copper 2 chloride, well, my sodium and my chloride are just kind of hanging out. They're not really doing any chemistry. They go from being dissolved in water to being dissolved in water. So no real change there. It's my hydroxide and my copper ions that are actually doing the chemistry to form some new substance. So chemists can often write what we call net ionic equations. And these are equations that only show the particles that actually participate in the reaction. So I'm going to highlight participate in the reaction. It's more efficient to show a net ionic equation in many instances if we're only worried about the chemicals that actually do a reaction. One last vocab word for this little section: particles that don't actually participate in the reaction are called spectator ions. Those are spectator ions because they're just chilling out, watching what happens, but they're not doing anything themselves. So here's the example, and this is our sodium hydroxide mixing with copper 2 chloride from above. You can see when I break this down from my complete chemical, so my complete, actually, this one up here is what you would call a chemical equation. And then down here, this before everything's crossed out, but where it shows all of the ions that are in solution, this is your complete ionic equation. And the key for this is substances that are the same in the products and reactants are crossed out. So your 2 Na plus ends on the products as 2 Na plus. Your 2 Cl minus ends as 2 Cl minuses. So since they are the same in the products and the reactants, they are considered spectator ions, and they can be removed when we write our net ionic equation. It's different when we look at your sodium hydroxide, or I'm sorry, your 2 hydroxide molecules, which end in your copper 2 chloride. They go from being on their own to being with the copper 2 chloride, and your copper, which is going to go from being aqueous to being in copper 2 hydroxide, right? So we can see the purple and yellow species combine to form an entirely new species, where your blue and green, they stay separate, and so they don't really do anything. So if we take out those ions that don't do anything, we're left with the net ionic equation. And again, this only includes the molecules that actually go through a chemical change in the process. And here we go. I have this visually as well. So you can see if we take our reactants, if I examine if I take a look at maybe just my chloride ions, you can see my chloride ion starts as just a green dot and in my reactants. And then when it goes to the products, it's unchanged. It's still just a green dot. Now I can also show for our sodium, right? So if I look at a sodium, it starts as just a gray dot. In the end, in our product, it's just a gray dot. So for both the sodium and the chlorine, they are going to start and end in the same place. If I compare that to my copper, it starts as a copper 2 plus, and it is actually going to end in a compound, in a solid compound. And it's the same for my hydroxides. They start as their own individual dissolved particle. And they're going to end part of this solid substance over here, your copper 2 hydroxide. So that's reactions that form precipitates. Now, there's 3 other things to talk about. So reactions that form water, many double replacement reactions actually can make water as a product. It's tough to spot this water because the water is usually the solvent in solution, and it's a colorless, odorless liquid that's fairly hard to detect. So if we look at an example, maybe you take some hydrobromic acid, combine it with sodium hydroxide, you form a water and a sodium bromide, right? So if I break that down and look at so this would be your reaction, right? So what are we looking at? Right, chemical equation. Look at this chemical equation, and the one below it is your complete ionic equation. Shows all the ions. And then if we cross out the ones that show up in both the products and the reactants, we cross out our bromide, we cross out our sodiums, and we're left with our net ionic equation, which is H plus combines with hydroxide, and it forms water, which is a liquid. So that's an example of a reaction that can form water. Two more examples. Some reactions can produce gases. Many reactions produce gases. These are very cool, very visual. These reactions are fun and very easy to drive to completion because the gas escapes. And you can see that is denoted in our chemical reaction with a gas as the product. Right? So these reactions are very common, very interesting, but just look for the gas as a product. Last thing, we can actually combine chemical reactions to simplify some processes that can be kind of complex. If you mix baking soda with hydrochloric acid, you're going to get this following reaction. HCl plus sodium hydrogen carbonate goes to carbonic acid plus sodium chloride. Your carbonic acid is extremely unstable, so right after your H2CO3 forms, it's going to undergo this decomposition reaction to form liquid water and carbon dioxide gas. So this reaction happens one right after another. So I'll just write one after another. As soon as the H2CO3 is made, it breaks apart into water and carbon dioxide. Well, and that actually, the second reaction is actually what forms the bubbles we see when baking soda is reacted with an acid. Now, it's important for us to remember these reactions occur simultaneously, or not simultaneously, but sequentially. So this happens, then this happens. And there's no pause. It happens immediately. So we can combine these reactions into one net reaction. So in order to do that, we'll take our two reactions, we'll put them over top of each other, and we'll add them together. And now you can see it's a H2CO3 as our reactant for our second reaction and as a product for my first reaction. So those two things are going to cancel out. And so for my overall net reaction, I'm going to take hydrochloric acid. I'm going to add it to sodium hydrogen carbonate. I'm going to form a sodium chloride, a water molecule, and a carbon dioxide molecule. And that's what I have pictured here. And so that's something if we need, we'll get more practice with it, but I don't think it's too heavily covered on the reagents. But I do want you to be aware that we can combine chemical reaction because it allows us to write fairly complex reactions pretty easily. All right, guys, that's all I have for this video. Thank you for listening, and I'll see you in the next one.